questions? All right, so let's start out with all right. Obviously, it's a relativistic problem. All right, so first off, we're dealing with length contraction here. The faster the object goes, the shorter it is. Thus, the rocket ship, the distance the rocket ship takes to the distant planet is less than the distance that Earth says the distant planet is. I guess proper wording would be the distance the planet goes to the rocket ship is shorter than the distance that the Earth says the strange planet is. So there's going to be some sort of contraction here. I know that with length, that the proper length is equal to gamma times the length. And you've got to fit numbers into it so that gamma can't be less than 1. Gamma cannot be less than 1. So which one's LP and which one's L?
I would guess LP is 10, because you usually say let the bigger be bigger.
Therefore, gamma is 10/9. And you went through this yesterday, so it should be relatively simple. I know that 1 over the square root of 1 minus beta squared is equal to 10/9. Solve for beta. What do you do?
I would multiply the whole denominator
You trailed off there.
over. I would multiply the whole denominator over the other side.
Okay, so 1 is equal to 10/9 times the square root of 1 minus beta squared.
And then divide by 10/9.
So 0.9 is equal to the square root of 1 minus beta squared.
And then square everything.
So 0.81 is equal to 1 minus beta squared.
And then just subtract over the 1.
Yeah.
So negative 0.19 is equal to negative beta squared.
And then square root.
I would recommend doing something else first before square rooting.
Divide by -1.
Why not multiply?
I guess, I mean, that works.
Now, so beta is the square root of 0.19, which is
Or
somewhere between 0.4 and 0.5. 0.447839.
0.435889. Yeah.
So what you're saying is I was wrong.
Not really, a little bit. Not really. Not very much.
So if you drive a little bit more than 43% the speed of light, you could do it. The trouble is, you get two different points of view though. You have the point of view of the garage is 9 feet long and the car is shrinking in size, but from the car's point of view, the garage is shrinking in size.
I have a question. So
Yeah.
when we say a 9-foot long garage, do we mean the car is 10 foot wide? Or are we going in sideways?
A 10-foot long car, so you've got
Headlight to headlight, kind of?
headlight to tail light, it's 10 feet long.
Okay. Oh, so it's trying to, okay.
So the only way you could fit in there is to shrink somehow. And you can do that with relativity. Unfortunately, from one point of view, the car shrinks, from the other point of view, the garage shrinks. So we need to somehow resolve this idea that resolve this somehow. So let's set up a scenario where we're dealing with somebody with a 16-foot meter, however, whichever unit you want to use. Let's see, how did I set it up? I used, we'll stick with feet. Nah, we're cool. Meters. All right, so we have really badly written notes. Just give me a moment, let me figure out where things are. Maybe Jack will return by then. Let's see, 10-meter long garage, good with that. 16-meter long pole, there we go, fine. This would be the rest length, or the proper length. That's a 16. And I want to fit it inside a 10-meter long garage, barn, whatever. The pole is going to be traveling with a speed. So both of their rest lengths, if I just had the pole sitting right there in front of me and I measured the different lengths, it'd be 16 meters long. If I measured the garage or barn or room, whatever it is, it's going to have 2 doors, whatever you want to call it. It's 10 meters long. So those are both rest lengths right there. Or proper lengths, if you will. Now the pole is going to be traveling. The velocity or the speed of the pole is going to be 0.866 times the speed of light. Now, the scenario is that when the left side of the pole gets inside the garage, both doors are going to close. I want to make sure I got that because we've already talked about simultaneity. Okay. So when the left side of the pole gets inside, from the barn's point of view, both doors are going to close. I got a door here, a door here. The left side's going to come in, both doors will close. So we've got 3 events here. I have event 1, I have right door closes.
No.
Event 2, left door closes. Event 3, pole hits left door. Because from the barn's point of view, the pole is shrinking in size, it'll fit in, and then it's gonna hit the, loop.
Right.
I'm getting my left and right backwards here. Left end of pole gets inside here, it closes. So I'm gonna make event 1, left door closes. Event 2, right door closes. And then pole hits right door. And just to hopefully minimize my confusion later on, I'm gonna write left and right.
So is the pole going in sideways to the garage?
No, it's going in long ways.
No, I'm saying like to the sides of the garage, not straight in. It's going.
Oh, from my point of view, we're looking at the side of the garage / barn.
Oh, okay.
Yeah. That was my question. The first thought I had, like that's the open end of the garage, but it's not.
Oh, that's
The barn or whatever.
That's the side. Now, to be able to get some sort of sense of what's going on in the two frames, we do need the Lorentz transformations.
I do have a quick question.
Yep.
Kind of related to this. So once it hits the left wall, does it like expand again? Like once it stops moving?
When it stops moving, then everyone's in agreement about the size, yeah.
So it just like sticks to the wall?
Well, presumably something's gonna break.
Oh, something. Okay.
I don't know, we're dealing with a hypothetical
Yeah.
situation, a thought experiment, so you can do whatever you want.
I-
It bounces, how about that? All right, the Lorentz transformations. I know that in the moving frame, that is equal to gamma times the rest frame minus VT. That was something that you dealt with yesterday, especially in problem number 7. And I know T prime is equal to gamma T minus Vx over C squared. Close parentheses. Again, if you're not sure whether it's going to be a plus or a minus here, then just sort of work through the scenario that I know that if I have an object moving, we synchronize the times. T equals T prime equals 0. This is my prime frame right here. Then it's going to move. I have some object over here, a distance x away, that after some time t, this has moved some time vt, and this is the distance x prime, which would be the distance from his point of view about where that is. And so x prime plus vt is equal to x, or x prime is equal to x minus vt. If you just do simple Galilean relativity, you know, just think through what it would be like in everyday life, that'll tell you the signs. I have my non-primed x and t together. I have the primes over on the other side. Because it's negative, that's a negative. All right. So, event number 1. We gotta synchronize clocks at some point. We gotta have something in common. So we'll just say when that left end gets into the garage here, or barn, again, I keep flipping back and forth. When it gets inside here, that's when the clock is 0. So event 1, so xt, event 1, x is, time is 0, we'll probably be dealing in nanoseconds here. And x is going to be, we'll make that our reference. So we're going to establish x is equal to 0 here. X is in that direction, and from the pole's point of view, X prime equals 0 at the left end. Event 2. Well, the right door closes when the left door closes from the barn's point of view, so that happens at 0 nanoseconds. And the distance is, well, 10 meters. This is the barn's point of view. And then event 3, gotta do a little bit of math here. From the barn's point of view, how long is the pole?
10 meters.
Pardon?
10 meters?
No.
No, can it see the whole pole, but not just like the end of it?
Yeah, I mean, you're the farmer, that's the barn, you're looking at the pole as it's sitting this way. More accurately, you're watching the pole come this way, but you're just slightly off so that you're close enough to being able to see the whole length without having to worry about relativistic effects when it's a two-dimensional problem. Pardon?
0 meters.
No, the pole does have length.
Is it 16
The
meters?
pole is not going the speed of light. 16 meters is what whoever's holding the pole is seeing, not what the person in the barn is seeing.
Is the pole facing like this?
Yes, there we go. We gave it a speed.
Or is the pole facing like this way? Forcing-
The pole, barn's here, pole's coming this way. If it helps, we'll make the barn sentient. The barn is watching the pole. Length contraction here.
Gamma times, like,
Pardon?
gamma times, like,
Yeah, so what's gamma?
gamma is 0.866.
No, that's V. Oh, actually, that's beta. What is gamma?
Time.
One point six?
Did you get 1.6?
No, 16 divided by 10.
We just do the.
All right, no, let's back up here for a second. Now, the problem that we just did with the car in the garage, we had the car just barely fitting in here. That's not the situation here. The pole is not just barely fitting in. There's gonna be some wiggle room there. Otherwise, the time of the last event would be 0 seconds. How do you find gamma? If I give you the speed, how would you find gamma?
1 over the square root of 1 minus V over C squared.
Yeah. Let's do that. So gamma is 1 over the square root of 1 minus 0.866 squared.
It's 1.9998.
2. I picked that number so that gamma would come out nicely. Probably should have gone a few more decimal points. All right, so gamma is 2, so from the barn's point of view, how long is the pole?
8 meters.
Yeah. So this pole is going 0.866 times the speed of light. Gamma is 2. It's coming towards it. From the barn's point of view, the pole looks like it's 8 meters long, which means it still has 2 meters to spare from the barn's point of view. Well, at that speed, how long will it take for that tip of the pole to hit the right door?
Not a long time.
Okay, I will agree with that.
Well, how long is it? How far is the pole from the barn?
The doors close as soon as the left end is inside the barn. So from the barn's point of view, we have barn, pole, 8 meters long from the barn. This is the barn's point of view.
You wanna know what's gonna hit the other door?
Yeah.
Oh, okay.
Is, actually, no, is it that equation where it's like proper time equals gamma times the other time?
No, you're going way more sophisticated than you need to. I have an object that's traveling 0.866 times the speed of light. By the time the door is closed, from the barn's point of view, it's got 2 more meters to go. How long does it take to travel that 2 meters traveling at that speed?
Just,
Distance to burn the speed?
Yeah. So the time that it would take, again, barn's point of view, so it's just regular old T, technically, T3.
7.7 nanoseconds.
So the time would be the distance over the speed. And so my event 3 happens at 10 meters, because that's where it is from the barn's, again, barn's point of view, and 7.7 nanoseconds. So we have these 3 events that are occurring, left door and right door close simultaneously, then pole hits the right door. From the pole's point of view, the barn's traveling at that speed, and the barn is coming at it shorter than it would, actually comes at it, looking like it's about 5, not looking like it's 5 meters long. And so we need to figure out what's happening from the pole's point of view. And yes, we do need to, for humanity's sake.